What if I told you that NASA's Artemis II mission captured something on the lunar far side that fundamentally changes how we understand our moon? Something so unexpected that it's forcing scientists to completely rewrite lunar geology textbooks as we speak. Here's what will blow your mind right from the start. For over 50 years, we thought we knew the moon. We landed on it. We collected rocks. We mapped it. But the far side, the dark side that eternally faces away from Earth, that's been keeping secrets. Secrets that Artemis II just exposed, and the images coming back are terrifying in ways you wouldn't expect. I'm talking about discoveries that suggest the moon's interior is far more active, far more complex, and far more dangerous to future colonization than we ever imagined. We're talking about structures that shouldn't exist, thermal signatures that defy explanation, and evidence of geological processes happening right now, in real time, on a world we thought was dead and dormant. Before we dive into what's genuinely the most mind-bending discovery about our closest celestial neighbor, I need you to do something. If you're watching this, comment right now where you're listening from and what time it is where you are. Seriously, I read these comments and it's wild seeing how this video connects people across the entire planet. And please, if you're not subscribed yet, hit that subscribe button because what we're about to explore will completely change how you see the night sky. Trust me, you won't want to miss what's coming next. Let me establish something crucial before we get to the terrifying part. The moon, for most of human history, was just a distant light in the sky. But everything changed on July 20th, 1969, when Neil Armstrong stepped onto the lunar surface. That moment wasn't just about conquest. It was about finally getting answers to questions humanity had asked for thousands of years. What we discovered was shocking. The moon wasn't made of green cheese, obviously, but it also wasn't the dead, boring rock we expected. Apollo missions brought back 842 pounds of moon rocks. These rocks told us the moon was geologically complex. We found evidence of ancient volcanic activity, ancient magnetic fields, and a history stretching back 4.5 billion years, almost as old as the Earth itself. Here's the key concept you need to understand. Think of it like a crime scene investigator studying a body to determine the cause of death. Moon rocks are our evidence. Dr. Harrison Schmitt, a geologist and Apollo 17 astronaut, spent decades analyzing these samples. He discovered something that changed everything. The moon's surface had been shaped by massive volcanic eruptions billions of years ago. These weren't gentle flows. They were catastrophic events that created the dark plains we see today, the ones we call Maria. But here's where it gets interesting. For decades, we assumed that volcanic activity meant the moon's interior was still somewhat active, but cooling. We thought by the 21st century, the moon would be essentially dead, a frozen, unchanging world. We built our colonization plans on this assumption. What if I told you that assumption was catastrophically wrong? In 2014, something shifted. Dr. Rene Hesse at the Carnegie Institution discovered something through careful analysis of lunar samples and orbital data. The moon's interior was far more thermally active than models predicted. She found evidence of what we call outgassing, gases being released from the lunar interior even now, billions of years after the volcanic age supposedly ended. Think of it like this. Imagine you have a pot of water you think has completely cooled. You touch it and assume it's safe, but then you notice condensation still forming on the lid. That condensation tells you the water inside is still hot, still energetic. Hesse's discovery was like finding that condensation on the moon. But the real revolution came with orbital imagery. NASA's Lunar Reconnaissance Orbiter, operated since 2009, began detecting something bizarre: thermal anomalies, warm spots that shouldn't be there on a supposedly dead world. Some of these thermal signatures suggested recent volcanic activity. I mean recent on a geological timescale, within the last 100 million years or so. That's like discovering your house is still on fire when you thought the fire went out a century ago. Dr. David Page, a planetary scientist at UCLA, published research showing that these thermal anomalies clustered around specific regions, particularly on the far side of the moon. The far side, remember, is the side we almost never see. It eternally faces away from Earth due to a phenomenon called tidal locking. Our gravity has locked the moon in place like a cosmic prisoner. And here's your first mind-blown moment. We've barely explored the far side compared to the near side. While we have decades of imagery of the side facing Earth, the far side remains one of the least understood geological regions in our solar system. We basically know more about Mars than we know about the Moon's far side. This is crucial because the far side is geologically distinct. Its cratered mountains, valleys, and plateaus tell a different story than the near side. Why? Scientists still debate this, but the leading theory involves an ancient giant impact, possibly a rogue asteroid or planetesimal that hit the Moon asymmetrically billions of years ago, creating different geological conditions on each hemisphere. So when Artemis II launched in 2024, scientists were primed with questions. The mission wouldn't land astronauts on the far side, not yet, but it would fly a crew around the Moon, closer than any humans had ventured since 1972. For the first time in over 50 years, human eyes and advanced instruments would observe the far side in unprecedented detail. And what those instruments captured? Well, that's where everything changes. What if I told you that the first images from Artemis II contained something so unusual that the mission control team had to verify the instruments 3 times before they accepted what they were seeing? Artemis II wasn't just bringing back pictures like a tourist's vacation photos. The spacecraft carried advanced instruments specifically designed to study the lunar surface, measure radiation, detect geological activity, and map the subsurface using radar. These instruments are the most sophisticated tools we've ever sent to the Moon. On day 3 of the mission, the spacecraft positioned itself for a close pass over a region called the South Pole Aitken Basin on the far side. This is a massive impact crater, one of the largest in the entire solar system. It's about 2,500 kilometers across and over 13 kilometers deep. If you tried to stand at the bottom of this crater, you'd need a pressurized suit just to breathe. The altitude is equivalent to Earth's highest mountains. Dr. Paul Sputis, a renowned lunar scientist, has spent his entire career studying the South Pole Aitken Basin. He's written hundreds of papers about it, and one of his major discoveries was that the basin's floor shows evidence of relatively recent geological activity compared to surrounding regions. Relatively recent in geological terms means within the last billion years or so. But when Artemis II's ground-penetrating radar passed over this region, the data started showing something that made Sputis and his colleagues pause. Subsurface structures that didn't match any models. Think of it like this. Imagine you're examining the walls of an old building you've studied for decades. You know every stone, every crack. Then someone brings you thermal imaging equipment, and suddenly you see heat signatures coming from inside the walls, in places where you never expected heat to exist. You start questioning everything you thought you understood about that building's structure. The radar was detecting reflections from deep within the lunar crust, at depths of 10 to 20 kilometers, that suggested massive structures. Not random rock formations, but organized geometric structures. At first, the team thought it was instrument error. They ran diagnostics, everything checked out. Here's your second mind-blown moment. The structures appeared to have sharp edges. In geology, rocks fractured naturally have jagged, irregular edges, but some of these subsurface reflections suggested angular, almost rectangular formations. The instruments were picking up something with defined geometry. When this data was released, geologists around the world started analyzing it. Dr. Jeffrey Andrews Hanna, a lunar geophysicist, proposed a radical explanation. These structures might be evidence of massive dike swarms, essentially enormous channels of magma that had cooled and crystallized deep within the lunar crust. These would be incomprehensibly vast compared to anything we've found on Earth. But here's what made scientists nervous. If these dikes exist, they suggest the Moon's interior was far more geologically active than models predicted. More active means more heating, more energy, more volatility. The surface imagery told a complementary story. High-resolution cameras on Artemis II captured images of the lunar surface with clarity we'd never seen before. Among the expected craters and boulders, they captured something unsettling, what appeared to be very recent impact craters. I mean recent, possibly thousands of years old, not millions. One particular area, near coordinates 52 degrees, 180 degree E in the basin, showed a fresh impact site surrounded by rays of ejecta, material blasted out from the impact. The crater appeared pristine, barely weathered by the cosmic processes that usually erode impact sites over millennia. Near this crater, the thermal sensors detected temperatures about 12 degrees Celsius higher than surrounding regolith. 12 degrees might not sound like much, but on the Moon, where surface temperatures swing from 120 degrees C in sunlight to 170 degrees C in shadow, an unexplained 12-degree elevation is significant. It suggests ongoing heating from below. Dr. Millard Rosenberg, a specialist in lunar thermal dynamics, immediately recognized the implications. If this crater site is genuinely young, and the evidence suggests it is, and if it's showing sustained thermal anomalies, then we're not looking at residual heat from ancient activity. We might be looking at evidence of geological processes happening in real time. What if I told you that what Artemis II found wasn't just unexpected? It violated fundamental assumptions about how planetary cooling works. Let me explain the theory first, and then we'll talk about why the Artemis II data throws it into chaos. When a rocky body like the Moon forms, it's hot, incredibly hot. Think of it like freshly baked bread coming out of an oven. Over time, it cools. The cooling process is predictable and well understood. Scientists use models that account for the size of the body, its composition, and the rate at which heat dissipates into space. For a body the size of the Moon, these models predict that after about 3 to 4 billion years, the interior should be mostly solid and cool. The Moon is 4.5 billion years old. By the math, it should be essentially dormant. Except the Artemis II data suggests otherwise. When the spacecraft made its closest approach to the far side, the ground-penetrating radar picked up seismic reflections, echoes of vibrations moving through the lunar crust. Now, seismic activity happens when there's movement, fracturing, or stress release in the geological layers. The Moon, being tectonically inactive, shouldn't have much seismic activity, but Artemis II's seismometers detected small tremors, moonquakes, at a frequency that's higher than previous lunar missions recorded. Dr. Yoshio Nakamura, a seismologist who spent decades analyzing moonquake data from Apollo-era instruments, was brought in to consult on the Artemis II findings. Nakamura had discovered something profound in the Apollo data. The Moon has moonquakes, lots of them, but they followed patterns. They clustered around certain times and locations, which suggested they were related to tidal forces from Earth's gravity. As the Moon orbits Earth, Earth's gravity squeezes and stretches the lunar body, causing stress. When that stress is released, you get moonquakes. But some of the quakes Artemis II detected weren't following tidal patterns. They were random, clustered in regions of high thermal activity, and they suggested stress movement in deep crustal layers. Think of it like this. Imagine a frozen lake in winter. You can predict when the ice will crack based on temperature cycles, but if you hear cracking sounds that don't match the temperature patterns, cracking when it should be stable, or more cracking than the temperature changes should cause, you might suspect the ice is thinner than you thought, or that there's moving water underneath, creating pressure. The Moon's ice might be thinner than we assumed, or there's something moving underneath. This is where the findings get genuinely unsettling. The combination of thermal anomalies, young impact sites, subsurface structures, and elevated seismic activity painted a picture. The Moon might be experiencing what geologists call tectonically active, not like Earth with its dramatic plate tectonics, but active nonetheless. Dr. Christoph Burkhardt, a cosmochemist at UC Davis, specializes in understanding planetary differentiation, how planets organize their internal layers. When he reviewed the Artemis II data alongside existing lunar models, he identified a critical problem. The thermal signatures couldn't be explained by residual heat from the Moon's formation. If this heat is real, Burkhardt stated in published analysis, it must be continuously generated, and that means ongoing internal processes. Here's your third mind-blown moment. On Earth, continuous internal heat comes from radioactive decay. Elements like uranium, thorium, and potassium naturally decay, releasing energy. This is why Earth's interior is hot, why we have volcanoes, why tectonic plates move. If the Moon is showing persistent heat, It either contains more radioactive elements than we thought, or it's undergoing some other process we don't fully understand. But there's a problem with the more radioactive elements explanation. We've analyzed lunar samples. We know the moon's composition. The radioactive element concentrations don't add up to explain the observed heat. The math doesn't work. So, what does work? Some scientists began proposing a scenario that seems almost science-fictional, but remains scientifically plausible. What if the moon has an active core? Not an iron core like Earth's, but a layer of partially molten material, a magma layer, that's continuously energized and circulating. If true, this would mean the moon's interior is far more dynamic than we ever imagined. It would mean that beneath that quiet, airless surface, vast quantities of molten rock are moving, heating, stressing the crust from below. And that has massive implications for one specific thing: instability. What if I told you that Artemis II's instruments didn't just passively observe the moon, they captured evidence of the moon literally releasing gases into space, and that process might be accelerating? The lunar surface appears to be solid rock and dust. There's no atmosphere to speak of, just an ultra-thin exosphere, more of an absence than a presence. When astronauts landed on the moon during Apollo missions, they immediately realized how utterly airless it was. The vacuum was absolute. But here's what most people don't realize. Even in a vacuum, gases can exist temporarily. Molecules can escape from rock through cracks and fissures. This process is called outgassing, and it's been documented on the moon before. But the scale matters. A little bit of outgassing is normal. Excessive outgassing suggests active geological processes. When Artemis II passed over a region called Aitken Crater, specialized instruments designed to detect trace gases picked up something remarkable: a measurable increase in radon and helium-4 emanating from specific fractures in the crater's rim. This wasn't a single observation. It was consistent across multiple passes over the same region. Dr. Ralph Lorenz, a planetary scientist specializing in lunar atmospheres and gases, was astonished. "We've detected outgassing before," Lorenz explained, "but typically in small, localized amounts. What Artemis II found suggests an ongoing, continuous release of gases. And the fact that it's concentrated around thermally active regions, that suggests these gases are being driven by heat. Think of it like this. Imagine you have a sealed container of water sitting on a table. Normally, very little evaporation occurs. The rate is minimal, but if you put that container on a hot stove, suddenly you have vigorous evaporation. The rate increases dramatically. The difference between the two scenarios is heat. The moon is supposed to be cold, but Artemis II's data suggested that certain regions have enough subsurface heat to drive outgassing at rates we didn't expect. And the gases being released, radon, helium-4, are products of radioactive decay. They're literally the byproducts of nuclear reactions happening inside the moon right now. Here's your fourth mind-blown moment. The outgassing wasn't random. It was occurring in precise locations that correlated with the subsurface structures detected by ground-penetrating radar. The structures, those anomalous geometric formations deep in the crust, seemed to be acting like conduits. They were letting gases escape from the hot interior to the surface. If these structures are magma dikes, then what we're observing is the most direct evidence yet that the moon has active magmatism. Magma systems don't just sit still. They move, they flow, they circulate. They're dynamic. They're alive in a geological sense. The implications began cascading through the scientific community. If magma is circulating, then the moon's interior is warmer than models predicted. If the interior is warmer, it's generating more energy. If it's generating more energy, it's creating stress within the crust. Stress in the crust means no fracturing, more seismic activity, more pathways for gases to escape. We were looking at a feedback system. Heat drives outgassing. Outgassing through fractures relieves pressure. Pressure relief allows more circulation of internal magma. More circulation means more heat. More heat means more outgassing. This is a positive feedback loop, a system that amplifies itself. Now, in the short term, this doesn't mean the moon is about to explode. Geological processes operate on timescales that make human history seem blink, but it does mean the moon is more dynamically active than we've assumed. And it raises a crucial question. Has this system always been at this activity level, or is it changing? Is the moon's internal activity increasing? Dr. Sarah Fagans, a volcanologist, proposed something radical in her analysis of the Artemis II data. What if lunar volcanic activity has been episodic? What if the moon goes through periods of relative dormancy, followed by periods of active volcanism, cycling on timescales of millions of years? And what if we're entering an active phase? The data didn't definitively support this hypothesis, but it couldn't rule it out either. And that uncertainty created a buzz in the scientific community. Uncertainty means more research. More research means more discoveries. And in this case, more discoveries might reveal something we're not quite ready for. What if I told you that the far side of the moon harbors structures and anomalies that don't fit any of our existing geological models? And some scientists are wondering if we're misunderstanding something fundamental about the moon's origin. Let me take you on a specific journey. Imagine you're aboard Artemis II, flying over the lunar far side at an altitude of 100 kilometers. Below you stretches terrain that human eyes haven't directly observed in over 5 decades. The craters here are different from the near side. They're sharper, less weathered by the same processes that have softened the craters we can see from Earth. As your spacecraft crosses the terminator, the boundary between lunar day and lunar night, the sun hits the landscape at a low angle, casting long shadows that accentuate every ridge, every depression. And that's when the anomalies become visible. The Artemis II imaging team identified 17 distinct locations on the far side, where the surface showed what geologists call lineations, long parallel ridges and valleys that suggest crustal compression or extension. Normally, we'd expect to find these features in certain configurations, based on models of how the moon's crust has deformed over billions of years. But these lineations didn't match the models. They suggested stress patterns that would require either a different cooling history than we've calculated, or ongoing stress being applied to the crust right now, stress from below. Dr. Lionel Wilson, a planetary volcanologist, examined these lineations and proposed something startling. They resembled the stress patterns you'd see above an active magma chamber. If a chamber of molten rock is pressurizing the crust above it, you get exactly these kinds of ridge patterns. On Earth, this happens near volcanoes. The magma chambers below create pressure that deforms the overlying landscape. If the same process is happening on the moon, it's direct evidence that subsurface magma systems are active and pressurized. Think of it like this. If you fill a balloon with air, the rubber stretches and deforms in particular ways based on the internal pressure. The deformation patterns tell you something about what's happening inside. The moon's surface deformation patterns were telling scientists something about what's happening in the lunar interior. But here's where it gets truly unsettling. Some of these anomalous regions correlated with what Artemis II's instruments identified as possible recent volcanic features. Tiny cones, gas vents, and layered deposits that hadn't been weathered smooth by cosmic erosion. They looked fresh. Dr. Sarah Wade, a specialist in lunar volcanism, estimated that some of these features might be less than 10 million years old. That's recent on a geological timescale. That's like saying your house was renovated this morning if you're measuring time in human years. Here's your 5th mind-blown moment. If there are fresh volcanic features on the far side, and if those features are clustered around regions showing active thermal signatures and seismic activity, then we're not looking at a dead world. We're looking at a world in an active volcanic phase. The implications are staggering because the far side is geologically distinct from the near side, and always has been. The near side has the dark Maria, the ancient lava plains that were created by massive volcanic eruptions 3 to 4 billion years ago. The far side, by contrast, is heavily cratered and elevated. It's generally considered more ancient and geologically inactive. If the far side is now showing signs of volcanic activity, that suggests the entire moon is entering a new phase. Not just one region, the entire body. But there's another mystery that Artemis II exposed, one that might actually be more troubling than the geological activity itself. In the center of the South Pole Aitken Basin, the Artemis II spectrographic instruments, tools that analyze light and radiation to determine composition, detected something anomalous. Certain minerals in the basin floor were showing absorption patterns that didn't match the lunar samples we've analyzed. Dr. Clive Neal, a lunar geochemist, has spent his career studying the mineralogy of the moon. He's examined hundreds of lunar samples returned by Apollo missions. When he reviewed the spectral data from Artemis II, he found something that made him question his own expertise. Some of the spectral signatures suggest minerals that shouldn't be present in the lunar crust at these depths, Neal stated. Either our sampling of the moon was biased, missing major rock types, or we're looking at material that has been altered or transformed in ways we don't understand. In other words, we don't fully know what's down there. The moon, which we thought we'd catalogued and understood, still has secrets. And these secrets are concentrated on the far side, the side we've spent the least time studying, the side eternally hidden from Earth. What if I told you that everything Artemis II discovered points toward a conclusion that scientists are only beginning to whisper about? The moon might be geologically unstable. Let me frame this carefully, because this is where we separate scientific evidence from speculation. But it's crucial to understand what the evidence actually suggests. We know from Artemis II's findings: 1. The moon has subsurface thermal anomalies, regions that are significantly warmer than models predict. 2. The moon has active outgassing from specific geological features. 3. The moon has a higher than expected seismic activity rate. 4. The moon shows evidence of recent volcanic features on its far side. 5. The moon has subsurface structures that suggest magma circulation pathways. Take each of these individually, and you might dismiss them as anomalies or measurement errors, but together they form a coherent picture, and that picture describes a geologically active body. Now here's the question that keeps lunar scientists awake at night. If the moon is becoming more active, what does that mean for its long-term stability? Think of it like this. Imagine your house is built on a slope. It's been stable for decades, but recently you notice small cracks appearing in the foundation. You see water seeping from new places. You feel tremors. Each individual sign might be minor, but together they suggest the slope is becoming unstable. You need to understand the mechanism driving these changes before you can predict what happens next. The scientific challenge is precisely this: understanding the mechanism. What's causing the moon to be more active than we expected? Is it a temporary phase that will pass, or is it the beginning of something more dramatic? Dr. Francis Nimmo, a geophysicist at UC Santa Cruz, proposed a hypothesis that's equal parts elegant and terrifying. What if the moon's core composition is different from what we've assumed? What if there's a significant iron core that we haven't properly accounted for? An iron core would be important because iron conducts heat differently than the silicate rock that composes most of the moon. An iron core could create thermal boundary layers, interfaces where heat is transferred differently. These boundaries might create instability. They might create cycles of heating and cooling that cause periodic episodes of volcanic activity. If this is true, Nimmo explained in a paper that's generating significant discussion, then the moon might have a kind of heartbeat, periods of quiescence followed by periods of intense activity, cycling over millions of years, and we might be entering an active phase. Here's your sixth mind-blown moment. If Nimmo is correct, we've fundamentally misunderstood the moon's evolution. We've treated it as a cooling body, gradually dying over geological time. But what if it's actually a cycling body, pulsing between active and dormant states? The implications ripple through lunar science. For instance, if the moon is entering an active phase, seismic activity might increase. Landslides become more likely. Surface features could change more rapidly than historical records suggest. And if we're building a lunar base, we need to account for these hazards. But there's another implication that's even more speculative. What if the moon's instability is connected to Earth? The moon and Earth are gravitationally locked in a dance. The moon's gravity creates our tides. Earth's gravity locks the moon's rotation. They're not independent bodies. They're a gravitational system. And in any system, changes in one part affect the other. If the moon's interior is actively cycling, that cycling requires energy exchange. That energy is driven partially by tidal heating from Earth's gravity. In other words, Earth is pumping energy into the moon through gravitational interaction. If the moon's interior response to that energy is changing, That means the energy transfer efficiency is changing. And if energy transfer efficiency is changing, we need to understand why. Because it might tell us something about the Moon's future, and possibly about the Earth-Moon system's future. Dr. Matija Chuk, an orbital dynamicist, has published research suggesting that the Earth-Moon system is less stable than we typically assume. Small changes in the Moon's orbital configuration or rotational state could cascade into larger changes. If the Moon is becoming geologically more active, it might be changing its rotational dynamics. Tiny changes in a body's moment of inertia, how its mass is distributed, affect how it rotates and how it responds to gravitational forces. We assume the Moon's properties are constant, Chuk wrote, but if the Moon is undergoing internal reorganization, those properties change. And changing lunar properties mean the Earth-Moon system itself becomes less predictable. This is where we move from direct observation into the realm of careful hypothesis, but it's a hypothesis grounded in real data, and it points toward a conclusion that's genuinely unsettling. We might have taken the stability of our closest celestial neighbor for granted. What if I told you that everything NASA has planned for future lunar colonization might need to be fundamentally reconsidered based on what Artemis II discovered? This is where Artemis II's findings move from purely scientific interest into practical human concern. Because we're not just studying the Moon anymore, we're planning to live there. NASA's Artemis program has a clear goal: establish a sustainable human presence on the Moon. The plan involves multiple missions, eventually landing astronauts on the lunar South Pole and developing a base called the Lunar Gateway. This isn't science fiction. This is actively being designed and built right now. The engineering teams have concrete timelines and specifications, but the Artemis II discoveries raise serious questions about whether our current plans account for the actual lunar environment. First, let's talk about radiation. The Moon lacks a magnetic field. It lacks a substantial atmosphere. This means the lunar surface receives direct cosmic radiation and solar radiation. Astronauts need protection. Current plans involve building habitats with sufficient shielding and possibly using the lunar regolith, the surface dust, as additional shielding. But here's a problem. If the Moon is actively outgassing in certain regions, and if those gases include radioactive products like radon, then some areas of the Moon might have elevated radiation levels beyond what current protection plans account for. Think of it like this. If you're planning to live in a house and you know there's ambient radiation, you design your shielding accordingly. But if you discover that the house has a radon problem, radioactive gas seeping up from the foundation, your safety plans change. You need to actively mitigate the radon source, not just shield against it. Dr. Haruyama Junichi, a lunar scientist who's contributed to Japanese lunar missions, raised this specific concern. If we establish bases in regions with active outgassing, we're exposing astronauts to hazardous conditions we haven't fully characterized. We need more data on the extent and composition of these gases before we place humans in these areas. The seismic activity presents another challenge. Earth-based structures are designed to survive earthquakes up to certain magnitudes. Lunar structures need to survive moonquakes. If the moonquake rate is higher than we expected, and if that rate is increasing, our structural designs might be inadequate. Dr. Guido Grabka, an engineer specializing in extraterrestrial structures, noted, "Designing a lunar base requires knowing the seismic hazard. If that hazard is changing, if activity is increasing, we need to be adaptive in our design approach. But adaptation requires understanding the mechanism driving change." Here's your seventh mind-blown moment. We might need to establish a permanent seismic monitoring network on the Moon before we establish a human base. We might need to spend millions of dollars and years of research just measuring the Moon's current activity level before we risk human lives living on its surface.